Okay, great. So I hope that you can see my slide right now. And my apologies, I think the bottom of the slide is cut off. I'm not quite sure why that is happening. But hopefully this won't really affect the talk today. Thank you everyone for joining this talk today. Thank you very much, Mohsen, for giving the introduction. And it's a pleasure, it's an honor to really be one of the faculties participating in the lecture series this semester. And it's really an honor to actually start our faculty lecture series. And we have a number of other wonderful speakers that are planning to give talks in the next 2 months. So please watch the calendar and join us again for these lecture series. So as Mohsen mentioned, today I'm going to talk about rockfalls, and specifically I'm going to focus on sensitivity of rockfall, frequency, magnitude, and rock wall retreat rates to observation duration. And I'm going to do that by looking at some data that we've been collecting over the last 5-6 years from laser scanning measurements in the European Alps. And the work that you see here, the core part of this work was done at the University of Tübingen in Germany. And a number of different people were involved in this project. And as I mentioned, it was a very long-term project and still continues to this day. And I was really lucky enough, fortunate enough to take part in this 5-year observation period for rockfalls. And I just like to take a moment to recognize and acknowledge the help of my field assistants. All of the work that you see here discussed, all of the data was measured and collected with the help of many different people in the field with me. And these guys are my friends, my colleagues, and they not only help with data collection, but they assisted me with cooking, cleaning up, even sometimes keeping away domestic animals like cows away from the scanner so that we could continue data collection without any interruption. So the work that you see here, there is a large group of people, especially students, masters, undergraduates, and PhD and postdocs behind it, who were very much supportive of my work in the field. So I want to take you to Lauterbrunnen Valley, away from Central Asia, for the next 40 minutes or so, and introduce this location to you. Just like Central Asia, it's a mountainous region. This is the European Alps. And as you can see in this image, is located sort of in the central southern part of Switzerland, in the Bernese Oberland. And the study area here is shown in red box. And as you can see, Lauterbrunnen Valley is a north-south narrow valley. The village of Lauterbrunnen, which is shown here by a black circle, is located about 10 to 15 kilometers south of a larger city called Interlaken. The village of Lauterbrunnen, it's quite small. The population is slightly over 2,000 people. But this location is highly popular for touristic reasons. So every year, hundreds of thousands of tourists come to this location throughout the entire 4 seasons for various activities, mainly skiing, hiking, or just admiring the beauty of the valley. And this is a deglaciated valley, which means that at one point there were glaciers here, and as they retreated, they carved this U-shaped valley that you can see here in the topography. And it's surrounded by some of the highest peaks of the European Alps. So I've put the Eiger, maybe you're familiar with the Eiger. If you're not familiar with the Eiger, perhaps you're familiar with the brand name North Face, which refers to the north face of the Eiger at the elevation of about 4,000 meters. And then other higher peaks here, Jungfraujoch, this is also another very high peak in the European Alps that locates very close to the Lauterbrunnen Valley. Of course, these elevations compared to what we have in Pamir and Hindu Kush and the Himalayas are quite not so high, but for the European Alps, these are very high numbers. So just to give you an impression of what this valley looks like, as I said, it's a flat bottom, deglaciated U-shaped valley. And as you can see, it's surrounded by vertical rock walls. So today I'm going to talk about at the rate at which these rock walls at both sides of the valley are retreating. They're basically moving away from the center of the valley. Now, Lauterbrunnen Valley is also well known for its waterfalls. There are more than 72 waterfalls that basically come off these very high cliffs. And the waterfalls and the river that drains the surrounding glaciers, as well as rockfalls, are the main mode of erosion for this valley. In terms of its geology, we are looking at limestone. So this is uniform lithology. All the rock walls here are made of limestone. This is Mesozoic Helvetic limestone, which was deposited as a calcareous mud about 140 million years ago. And then it was deformed during the Cenozoic alpine orogeny. Now, following the last glacial maximum, this was about 10,000 years ago, the R glacier system basically retreated to the higher grounds, and that's when this U-shaped valley became exposed. And you may also notice some of the talus deposits here at the bottom of these rock walls, and these talus deposits are indicative of previous rockfall activities in this region. So here an example of a rock wall. As you can see, it's vertical. Oftentimes, these rock walls are about 500 to 800 meters long from the bottom of the valley floor. And as you can see, there are waterfalls coming down, perhaps making some sections of the walls wet. The moisture oftentimes travels with the wind away from the locations of the waterfall and lands on other parts of the rock wall. And in some places, you can also see some jointings and fractures and evidence for previous rockfall activities. And of course, you see houses, farmlands, and this is why we really care about monitoring rockfalls in this valley. It's a populated valley. Of course, it's a village, but you get a lot of tourists, and even being a village, most of the land in the valley is being used for agricultural purposes. So there are definitely infrastructure there that could be affected by rockfalls. And we've seen that in the past. So if you go back in time to about 130 years ago, there was a massive landslide where a section of the wall was collapsed and basically covering a very large portion of the valley. In the historic records, it said that for months, the dust from this rockfall activity was actually in the air and spread through a very large distance. And much of the agricultural lands and farmlands were covered by the material that was deposited due to this rockfall. So we're talking about over 10,000 cubic meter of debris flow that basically came down and formed these cone-shaped talus deposits. We also see smaller rockfalls. These are more recent, and you can see them throughout the valley. And as you can see in this case, some of the infrastructure have been affected by these rockfalls. So it is very important to study these rockfalls, to understand their behavior, and to be able to say something about their future occurrence in the valley, so that any kind of development that takes place in the valley or the current development that's already taking place is protected against these activities. So if you're not already motivated enough by this landscape and by the fact that rockfalls happen here quite frequently, I have two other reasons to bring your attention to this landscape, bring your attention to Lauterbrunnen. So for those of you who are the fan of the Lord of the Rings, the Tolkien's based the Elven Kingdom of Rivendell on the landscape of Lauterbrunnen Valley. So as you can see, there is a drawing of Rivendell, and it is quite representative of many of the features that you see in Lauterbrunnen. So that's just a fun fact. And also, if you are not a fan of Lord of the Rings, but you are familiar with James Bond's movies, one of the older or earlier James Bond films, which was produced in 1969, was also filmed in the Lauterbrunnen Valley, and all the ski scenes that you might be familiar with if you have seen this movie were filmed in Lauterbrunnen. I was watching this movie quite recently. Instead of focusing on the script and the narration and the movie itself, I was just fixated on the walls of Lauterbrunnen Valley, looking for evidence for Rockfalls, since the historic data is not quite complete from this valley. So I was trying to see if I could find some evidence in the movie. So with that, let's get started. So the main problem that I'm going to focus on during this lecture is how do rockfall retreat rates and rockfall frequency magnitude relationship vary over different time scales. And if you're unfamiliar with those terms, please do not worry about them. I will go over them, and hopefully you have a better understanding of these terminology. And when I say different time scale, I am referring to 1 to 10,000 years. So it's quite a large time span that we are looking at. And I am specifically interested on two things to address this problem. First, to evaluate the frequency magnitude relationship over different time scales. So we're going to look at monthly versus yearly, and in this case, 5-year average rates. And then investigate rock wall retreat rates, so how slowly or how quickly these walls are retreating away from the valley, from the center of the valley, over different time scales. As I mentioned, this is over 1 to 10,000 years. And to do that, I use a method called laser scanning. And you can see our laser scanner here to the left side of this image. This is an Optec ILRIS long-range laser scanner. And one great thing about this laser scanner is that you can obtain high-resolution data from large distances, hence the long range. So we usually have about reflectivity of 80% at 3 kilometer distances, which means that if the wall is located about 3 kilometers away from the scanner, we get a reflectivity of the laser beam up to 80%. So we can get really high resolution imagery of the walls, despite them being very close, very far from the scanner. And using this laser scanner, we set up 22 scan positions, and that's what you're looking at here on the right image on this topographic map. And we try to distribute these scanning positions equally on both sides of the valley so that we can monitor walls on both the east and the west side of the valley. As I mentioned, this is the north-south valley. So the scans that are named with the word with the letter W are looking, those are positions where we are looking at the east wall, and also the ones that are labeled with the letter E. Those are the scan positions that are basically facing towards the west wall. And doing this, we are able to get a continuous surface image of the surface from both sides of the valley. So no section is left behind. And there's quite a lot of overlap between these scans so that we can make sure that we get the entire valley, but also we get different scans from different angles in case we might be missing some sections of the wall due to shadow effect. So we did this over 19 field campaigns. That meant that I went to this area 19 times over the period of five years. And every time I went there, I basically spent about a week there with my colleagues, and we scanned the walls during that week. Now, once we have the data collected, the raw scan data, we use a software called Parser. This is a software that comes actually with the scanner, and it prepares the files in a format that is readable by a program called JRC. In this program, we are able to actually do some post-processing of the data, which means that we get rid of all the noise and all the unwanted things that we are not interested in, including vegetation, because that's also something that if you're looking at detecting rockfalls, we don't want to really look at changes in the volume on the rock wall due to vegetation. So we remove the vegetation manually. And once we do that, we pre-register our scan, which means that we bring two scans that were taken at different time intervals of the same section of the wall. So we bring those two scans together and we try to align them by manually selecting at least 3 points. Generally, I select over 10 points, but it's enough if you take 3 points. And basically, you try to get these 3 points on the two scans as close as you can to one another. And then once you have that manual alignment, you basically, in the registration step, you find the best fit using an algorithm there, and then you are able to create mesh surfaces of those two scans. These are smooth surfaces of the rock wall, and these are triangular meshes. And later on, we use these triangular meshes with a tool that's called an inspection tool. And this inspection tool basically takes the difference between the two scans, meaning that if there are any changes between those two scans, we are able to detect them at this stage. So the two scans are being compared with one another. And of course, those differences could be either material being added to the wall or material being taken away from the wall. And that's the cut and fill algorithm that basically tells us where in our walls we have lost materials, perhaps due to rockfall, which is what we're looking for, or we have gained material, perhaps due to snow deposits or vegetation growth, and that could also be. But it's important to distinguish between material loss and gain because they both give us the same signal when we difference our scans. So to distinguish between the two, we have to rely on photographs. And that's why we take photographs in the field. So just to show you what that looks like, here are two scans, two point clouds that are being aligned to one another. After they're aligned in the inspection tool, we basically difference the two to figure out material gain or loss. And that difference is shown in pseudo colors here. So every time you see a blue color here, it means that there's absolutely no change in the rock wall between two scans that were taken at different times, which means that there was no rockfall. And if we see a change, we see it something similar to what you see here in the right side of this image. So if you look at the left side of the image at the bottom left corner, that's where I noticed that is the only place we were able to detect some changes. And then I looked at it a little bit more carefully, and when you see the very red color, that means that that's where you have the highest amount of volume being taken away from the wall. And as you go away from that center, the colors get lighter and lighter. And it's surrounded by blue area. This blue area is the area that's unchanged. So it was not affected by that rockfall. And of course, then I don't know if this is a gain of volume or a loss of volume. Then I looked at the images that were taken before and after, corresponding with the scans that were being differenced. So here in this image, we are looking at a photo that was taken on June 2013 and a photo that was taken on July 2012. And these scans also correspond with those two different campaign measurements. And looking at these photographs, we were able to see that, yes, indeed, where we see some changes in the rock wall, we also see those changes as the rock fall in photographs. Then we can say with more certainty that this was indeed a rock fall. And of course, then we can calculate the volume of it. And in this case, we're looking at something around 120 cubic meter. So we did this processing of data for all of our data sets, and this is what we get. So what you see here on the right, up on the top, we have the west wall, on the bottom, we have the east wall, and every circle here shows the location of a rock fall that was detected by TLS measurements. Now, the circles that are in yellow were part of the study that was done by a colleague of mine, which was published in 2015. And I continued that study, and basically what I measured over the last 5 years are shown here in red circles. And the size of the circle corresponds with the size of the material that was lost due to rockfall. So you see there are lots of small events here between 0.03 to 2 cubic meter, and then there are several larger ones. In fact, about 3 or 4 over 120 cubic meter of material lost in the last 5.2 years. We excluded this section of the wall, though we scanned it and processed the scans, but we excluded this section of the wall on the east side, mostly due to the fact that Mount Schwarzmünch is located quite far away from our scanner, and the angle from our scanner to the wall is quite steep. And these two factors really affect the resolution and the amount of error that we have when we are aligning scans. And therefore, we decided to take away this part of the wall and not include it in our frequency magnitude calculations, simply because we didn't really trust those values. They had large error bars. So overall, we detected over 300 events over a period of about 5 years. Now here is the summary of the rockfall data. All I want to say about this is this last row. So we basically monitored the activity between 2012 and 2017. We were able to identify over 300 rockfalls with very high accuracy, both on the east and the west wall. And the smallest event that we detected was 0.03 cubic meter, and the largest one was 267 cubic meter in this time period. Now, what do we do with that? We use that data to basically create a frequency magnitude relationship. And as the title says, it's basically we're looking at the size or the magnitude, and in this case, volume of the rockfall on the x-axis, and also the frequency of that event. So on the y-axis, we have the cumulative number of events per year. So this is a log plot, and every little circle, dark circle that you see here correspond with one individual event that we detected over these 5.2 years. And looking at this plot, you might immediately notice that there is a specific shape to these values. First of all, this part of the plot looks very linear, which means that you can fit a line through your data points. But if you get up here, you see that you're diverging from that linear behavior, and you're sort of flattening your line here. So that is known as, where you see this flattening, or the curve, is known as rollover, which means that there is a volume of rockfall below which your data is not following a linear behavior anymore, and it's basically curving a little bit and falling a little bit lower. So in order to find the frequency magnitude relationship for this plot, we first need to determine what this value is. And this value, again, is the volume. And anything below it does not follow any particular pattern. But anything above it, any volume larger than that, seems to be following a linear, and in this case, a power law relationship. So what we want to do is to remove all those rockfalls that are smaller than our rollover volume, and then focus on what we are left with. So what you see here in red are the rockfalls that we remove. And once we do that, we calculate a range of corresponding power law fits. So these are a number of lines that are fitted to the remaining of the data here. And this is the form of the power law, and the prefactor A and negative B, these are our power law exponents, and are quite important, especially in terms of understanding long-term volume loss, and also when we calculate return intervals of events in the future, which is important for hazard assessment. And we use the maximum likelihood estimate to basically calculate these corresponding power law fits. So what you see here in blue is those corresponding power law fits that fit the data, and we get an equation for that. And this equation has a form of a power law, so something to the power of something, right? So the V is our volume, and we see that we have a range for our A value and a range for our B value. Now, to see if our power law relationship is sensitive to observation timescale, we also plotted data from an earlier study from Lauterbrunnen, which covered data for over a period of 1.5 years. So what you see here in green and the corresponding power law equation only relates to data that was collected over a shorter time period. And what you see in blue is what we collected over a 5-year period. And looking at these two plots, they look very similar to one another. And this is interesting. I want you just to notice 3 things here. One thing is that the power law exponents, so if you look at these 2 equations, they are in agreement within error. So our exponent A and B are within the same range. And the difference that we see here is basically there is a systematic decrease in the frequency of the smaller events in the 5.2-year data sets. So as you can see, these black dots, which correspond with the longer data sets, have shifted a little bit lower than the gray ones above them. And so that's one of the differences that we can see. And the other, so basically the number of smaller events detected seems to be a lot higher. The frequency of them seems to be a lot higher in the short term or the 1.5-year data sets. And then we also notice that in the longer term data set, we are able to capture larger events. So these 3 points and the ones that you see here, these are the larger magnitude rockfalls that were detected in the long term or 5.2-year data sets. And this simply could be due to the stochastic nature of rockfalls, but we'll discuss this a little bit more later. So now let's take a look at the rockfall retreat rates over different time interval. So now that we have all the information in terms of rockfalls in the last 5.2 years, and we know what the volume is, we can basically calculate the modern day, present day retreat rate. And in this case, it's a 5-year average retreat rate because we collected data over 5 years. And to do that, we need the total rockfall volume. And of course, when then we divide that with the rockfall area and we normalize that to 12 months, and then we get a retreat rate. And we've done that, and this is the rate that we get. So in the 5 years that we've been observing these rockfalls, basically the west wall has been moving at a rate of about 0.08 millimeters per year, and the east wall at a rate of about 0.03 millimeters per year. These 2 rates might be different, but in fact they're not when you take into consideration the rockfall area. Remember that we took away a large portion of the east wall, and hence this number seems to be smaller. But when we basically take the area into account, they are very much the same. So there is hardly any differences between the retreat rates, modern day retreat rates between the 2 sides of the valley. We need to keep in mind that this rate is sensitive to the time scale of observation, which is about 5 years. So large events generally don't happen so often. So we end up capturing lots of smaller events, but very few, if any, during long-term, during the short-term observation time. It's also sensitive to the detection limit for individual events. So our scanner cannot detect anything smaller than 0.01 cubic meter. And basically, if there are rockfalls of that size, we are not able to see them. And one might say, well, that's really tiny rockfalls. Who cares about them? And although that's true, maybe in terms of hazards, this is not much. But in terms of creating a robust relationship between frequency and magnitude of an event, if you're getting a lot of events of these size or smaller than this size and you're not detecting them, then that relationship is not very robust. So this could play a role. So to get around this and to get a retreat rate that is maybe more representative of this area and is not sensitive to these two things that I've listed here, we basically looked at the power law retreat rates. And we get the power law predicted retreat rate from the frequency magnitude relationship that I discussed earlier. And we get a rate of about 0.14 to 0.22 millimeters per year, so higher than modern rate. And to do that, basically, we use this equation. We integrate the frequency density of rockfall magnitudes from our TLS data sets, and we multiply that by the event volume here. So the integration boundaries here, the V minimum and V maximum are set to these two numbers. The minimum volume is our rollover volume, which I discussed earlier. This is the volume below which we are not following a linear relationship anymore. The maximum volume is set to 10,000 cubic meter, and this is the volume of the largest recorded historic events. And then, of course, our A and B values, those are our power law exponents, which we get from this equation. And knowing all of these parameters, we can calculate the total volume, divide that by the Rockfall area, and normalize it to 12 months. We get this rate. So this is how the power law predicted rate, which is an intermediate timescale rate, is calculated. So the third approach and the final approach we took for calculating wall retreat rates, we used talus deposits. And by looking at that talus deposits, we can actually say something about the retreat rate of these walls since about 11,000 years ago. So talus deposits are good indicators of long-term rockfall activity in any region. But to do that, we need to first figure out where they are and map them carefully. So in this case, we have taken only 3 talus deposits, 2 on the west side of the wall and 1 on the east side. We also looked at another 2 talus deposits, but later didn't use them in the study because they had very complex morphologies and there was some evidence of incision by their waterfalls. So we didn't want to get a geometry that has already been affected by other erosional processes. So we focused on talus deposits that are simple in geometry so that we can get a more accurate estimate for the volume of the talus deposits. Here's an example of what a talus deposit looks like. So you can see the rock wall in the field here and the fresh talus here. Generally, the slope of these talus deposits are about 30 degrees, and you can see fresh rock falls already deposited on them. So what you see on the surface are indicative of modern day rockfall activity, and as you go lower, deeper into the talus, you're hoping that the evidence of the past rockfalls are there, and you can use that evidence to say something about how fast or how slowly these rock walls have been retreating over these last 11,000 years. We use a very similar method to calculate the volume of these talus deposits. So we use our TLS, our scanner data, plus some digital elevation models, in this case 2-meter resolution. We bring all that data into JRC, so same program as before, and we delete the vegetation, get rid of all of that, and we do that to create a smooth surface. We use a tool that's called topographic meshing tool within the software, and that gives us these smooth mesh surfaces of the talus deposits. With that information, we also get some of the geometric information from the taluses. Now, if anybody wants to do this in the right way, and if you want to get accurate numbers and not just estimates, the best way is really to go to the field and do measurements of these talus deposits. However, we didn't do that. We just wanted a rough estimate of that because we are comparing rates here. So we just used a very simplified talus geometry. And this was part of the master's students' studies that actually allowed us to calculate the long-term retreat rates and compare it with the modern rates. So what we did basically is to estimate where the base of the talus is, where it meets the rock wall, and the top surface, that's the accurate one. That's the one that we can actually measure and see quite well with the TLS and the digital elevation model data. And then we calculate the volume of the talus deposits. And once we have the volume of the talus deposits, we can use this relationship here to measure the retreat rate over the last 11,000 years. And as you can see, this rate is about an order of magnitude higher than the short-term rate. So it's about 0.27 to 0.38 millimeters per year. So it's quite faster than what we measure today, or the 5-year average. So to get this rate, as I mentioned, we have the volume of the talus deposits. We multiply that by density correction factor. This is basically a number that allows us to take into account the density difference between the talus materials, which are quite fragmented, and the intact rock wall above it. And for limestone, that value is generally about 0.77. So that's where that value comes from. We know the rock wall area quite well because we use the TLS data to measure that. And of course, the talus production rate is set to 11,000 years. This is basically the time that is this initiating time, the start time of when the talus deposits started to accumulate. And we get this time basically by assuming, and this is a very strong assumption, that the glaciers basically left the valley by this time. So anything that has accumulated since then is due mostly to rockfalls and not to any other processes associated with glaciers. So taken together, we notice that the long-term rates are much higher than the short-term rates. And we can say that by looking at these 3 rates that we measured over 3 different time scales. So the 5-year, the power law predicted, and the 11,000 years based on talus estimates. And you can see that these rates are generally a lot higher, and the longer-term one is even an order of magnitude, or more than an order of magnitude, larger than the 5-year retreat rate. Now, of course, the next thing is why? Why do we have this difference? What processes maybe are in effect or have been in effect that really creates this change or this difference between rates? So there are possible reasons. One simply is that due to undersampling of events in 5 years. So the 5-year data set is just not long enough to capture all the events, and especially the large events that happen in this valley. As you can see, there are events, very large events that have happened in this valley before, but the 5-year data set is not going to capture those events. It's only going to focus on the smaller events. So one possible reason is simply due to the undersampling of events, which is quite reasonable. But the other 2 and 3 are more related to tectonic loading or stresses and the changing of climate in this area. And since this is a deglaciated valley, debuttressing after glacial retreat is a high possibility. And by that, I mean, when you take away the glacier from a valley, you basically also take away all that ice that used to support the rock walls from the sides. So when you remove that ice, the rock walls on both sides of the valley, they are no longer supported. So your confining stresses, horizontal stresses, they release stress. And as they release that stress, as they relax a little bit because they don't have that support anymore, they create joints. And later along those joints, you can get rockfalls. So one could be due to that, and that's quite common for valleys that have been deglaciated. This has been documented in other places in the Alps. But the other reason could be due to the changing climatic conditions that followed in late Holocene. And we have periods of cold phases as well as periods of humid phases since 11,000 years ago. And these periods, it could be that they enhance rockfall activity for short time intervals in the last 11,000 years. And often the main triggering factor is due to freeze thaw activity or permafrost degradation. So as you go through these changing climatic conditions in the last 11,000 years, you prepare the walls for rockfalls. You enhance and increase rockfall activities during those specific periods in the 11,000 years. Or it could be a combination of all these three reasons. So in summary, we looked at how rockfall retreat rates and rockfall frequency magnitude relationship vary over different timescales. We noticed that the frequency magnitude relationship is not sensitive if we are looking at observation period of 1.5 versus 5.2 years. And this is quite useful actually, because this means that you don't necessarily need a long-term, meaning 5 years of data collection in order to produce a robust frequency magnitude relationship for hazard estimates. And that a frequency magnitude relationship constructed over 1.5 years does as well as one that does in 5.2 years. So this is quite good. We don't need really a long-term study to have this general frequency magnitude relationship. We can help us with estimating the return interval of events in the future. In case of rockfall retreat rates, we noticed that they are indeed sensitive to observation timescale. Short terms are much smaller than long-term rates, and this is important. We need to take that into account when we are thinking about retreat rates or erosion rates of these surfaces. The timescale plays a major role, and oftentimes the timescale also indicates the mechanisms for which you get higher versus lower erosion rates. So this is my last slide. I have put here the two main publications that have come out of this study. They're both open source, and if you're interested to learn more about them or more about the details of these studies, you can look them up. One was published just earlier this year in geology, and as part of this publication, we've also made all the point cloud data and the MATLAB codes that we use for processing and creating this frequency magnitude relationship available to everyone. So you can access these openly without any issues, but if you want the point cloud data or the MATLAB codes, you can just contact me directly and I can make sure that you have access to those as well. And there's also another paper that I co-authored with some colleagues from GFZ in Potsdam, Germany, which looked specifically on seismic monitoring of these rockfalls in the Lauterbrunnen, but only focusing on some sections of the walls and not the entire valleys. But that's also a very interesting publication. And it could have some implications for studying and understanding rockfall activities in the Pamir and throughout Hindu Kush. And with that, I will end this talk and would be happy to take your question. Thank you.
Okay, thank you very much, Solmaz, for this very interesting talk. Okay, we can see that there are lots of things covered actually here. And I think our colleagues from different departments, such as mathematics or computer science, they can find something relevant to their studies or specialty. And I hope that we can actually work on these collaborative works in the future. Okay, as Solmaz said, if any question, please, you can ask your questions. There was a question, Solmaz, in the notes, in the chat. I tried to answer it, but I'm not sure if I answered it actually in a wrong way. This question was from Azmat. Azmat, are you going to ask the question again so Solmaz can give a much better answer to this question? Hello, Azmat. Okay, I'll repeat the question. Solmaz, the question was the difference between landslide and rockfall. What is the difference between landslide and rockfall?
Okay, that's a very good question. So when we use the term landslide, oftentimes people include rockfalls in landslides, so a more general term. But those who study these different types of mass wasting events are very picky about them, and they do like to separate them. And in this case, I do separate them. So landslide, as the word landslide says, you get basically a slide of a very large portion of a section of land. And it can happen in many different ways. In this case, rockfalls are very different from landslides, especially in Lauterbrunnen valleys, because you get a part of the wall sort of separating along pre-existing joints, and they sort of fall down vertically. So they don't slide, they don't, they might topple around, but generally it's just a vertical fall from the time that they get released to the time that they land on the talus slope. But with the landslide, you have this massive slide, really slide, not necessarily this vertical fall of materials from the cliffs. And in Lauterbrunnen, what we really focused on were rockfalls. Though there was an example of a, they call it a landslide, but this is, again, it's a massive rockfall failure that brought down not only the section of the wall, but everything above it. So there was some vegetated section at the very top of the cliff that also slid down with the rest of the unit. So I hope that I answered that question correctly.
Thank you. Yeah, thanks a lot. I can see some questions in the chat box. Could you please ask your questions directly here instead of typing it in the chat box, please?
Okay. Can you hear me?
Yes.
So my question is, what is your suggestion or what we as humans can do to stop rockfalls if we are capable, if we can?
Yeah. Very good question. There are certain rockfalls that no matter what you do, they're going to happen there, because it's not due to human activities or anthropogenic effects, as we call them. For instance, in the Lauterbrunnen Valley, these rockfalls, as I said, are due to just the fact that the glacier, left the valley, and it's really changed the morphology and also the stress that is basically used to keep these rock walls together, and now that stress is reduced and the rock walls are more prone to rock falls. So there are certain kinds of rock falls that we cannot stop them from happening because they're just triggered by mechanisms that we have hardly any control over. We can reduce and mitigate damage related to these hazards, and there are a number of different mitigation strategies that can be put in place to make sure that infrastructure, humans are protected from such activities. However, there are also types of landslide mass wasting events, including rockfalls, that are induced by human activity, and those are the ones I think that you're maybe asking more about. And for these, yes, there's a lot that can be done. So oftentimes deforestation is one of the main reasons for mass wasting events. So by unsustainably and unthoughtfully clearing out forests and vegetation that keeps together the landscape, we basically make the landscape more prone to such activities. So deforestation is one of the most common reasons for landslides or mass wasting events, combined with precipitation and maybe earthquakes, especially in case of Pamir and Hindu Kush. All you need is a little bit of an instability in a slope, and that instability, even though it might be very little with an earthquake, it has the potential to really create a massive mass wasting event. Another thing is, just developing infrastructure such as roads, changing the landscape due to development without really thinking about what that change really means, how that change really affects the stability of the slopes. And if that is done without thinking, then of course that can enhance rock falls as well. So we need to be very careful when it comes to development and try to be as informed as we can before develop a place either for road or any other form of development to make sure that these hazards are mitigated and addressed before they occur.
Thank you.
Okay, thank you very much, Solmaz. I can see two more questions. Please, could you ask your question here? Doiraj and Hoja.
Thank you, Solmaz, for the interesting presentation. You did discuss about the debuttressing and the climate change as one or two of the main factor influencing your calculation of retreat rate. I wonder, you did not speak about the frequency of seismic activities. So, I mean, do you hold another view?
No. It's good that you point that out, and that was actually one of the papers that was published about this work, and I think the reference was shown here, Strunden et al. Back in 2015. That paper was purely focused on the triggering mechanisms for rockfalls in Lauterbrunnen, and they ruled out seismicity for this specific valley. Of course, seismicity is a triggering mechanism, especially for rock walls that are already, at a point of failure. And so that can be a reason if you're looking at a different part of the world. But for Lauterbrunnen Valley, seismicity doesn't seem to really affect or trigger rock falls there. And there was hardly any correlation between the seismic data and the number of rockfall activities and the timing of them during the observation time that we considered. So we did look at that and a few other factors related even to climate, to weather, such as precipitation, temperature, and we didn't find any strong correlation between them. So I try to focus right now on parameters or conditions that seems to be really the main mechanisms here for enhanced rockfall activity, because the other ones, so far, no strong correlation.
Okay, thank you very much, Solmaz. So Hoja, can you ask your question, please, here?
Salam, Solmaz. It's a pleasure that once again we see here, and nice to see you after long years back. We have met in Kabul. Thank you for your amazing presentation and lectures. So my question is, did you find out any critical factors that influence or impact on the gain and loss of rockfall volume?
Do you mean what affects the volume of the material that the volume of the rockfalls that we have detected? What are the major players for affecting the volume? Okay, so if that's the question,
losing, gaining the loss or the mass of the rocks.
Yeah, I mean that's a really good question, and we didn't really look into it carefully to see why sometimes we have these smaller rockfalls and why we have slightly larger ones. What is for sure true is that there are definitely more smaller events. And in these 5-year data sets, the majority of our events were actually about 1 cubic meter in volume. And we only have very few larger events. So smaller events definitely play a major role. And I think we sometimes get really focused on larger events because those are also events that have higher impact on human societies. But these smaller events, when you take into consideration the main contribution for all of them, because there's so many of them, we should actually pay attention to them, and they are quite important. I am not sure about Lauterbrunnen Valley, but smaller events oftentimes are associated with these freeze and thaw cycles that you see. So in seasons, for instance, when you are transitioning from winter to spring, this is the time that oftentimes in other parts of the world, and also I think in Lauterbrunnen, generally we see this pattern that you get these smaller events more, you detect them more, and this could be explained by the freeze and thaw cycle. So you have the water that was basically inside of the cracks or joints in the rock wall. And as it expanded, and froze during winter times, and then thawed and, went away, and you're basically changing the internal stresses in the rock wall. And by changing those internal stresses, if you're doing that near pre-existing joints that are very close to failure, you don't necessarily get very large falls, but you can actually trigger very small rock falls. And this has been observed in other places for small volume rock falls. And it's one of the main contributors actually to small rockfall activity in many mountain areas. But we didn't really look into the actual mechanisms between small and big ones. But my thinking would be that you have to look at the jointing and the fracture surfaces. And oftentimes these really massive rock falls, they occur near or at these pre-existing joints that are, they just need a little bit of a triggering either by climate or seismicity, as we mentioned earlier, to trigger a large fall. And if that fall, if this triggering occurs near a very large joint that covers a very large portion of this rock wall, then there could be a possibility for a larger fall.
Thanks a lot.
My
Okay,
pleasure.
thank you very much, Solmaz. Any other question, especially from our good students?
Hi, Mohsen. If you consider me as a student, I have a question.
Hi, Ben. Please ask your question.
Yes, thanks so much. That was very, excuse me, very interesting presentation about Rockfalls. I'm having a little bit hard time to understand the duration of your sampling period, which is 5 years, and extrapolating it for many years. As you know, other external stochastic parameters like precipitation, earthquakes, which we consider higher magnitudes to happen 1 in 50 years or 1 in 20 years. For sure, we couldn't expect to see in this shorter 5 years of sampling period. How confident you are in extrapolating this information or samples from 5 years to larger time period? Can you elaborate on that a little bit?
Yeah, this is a good question. So, I mean, there has been a lot of rockfall inventories that span, much longer time period than what we are covering here. So possibly even over, 30, 40 years in some cases. And not any rockfall inventory, is perfect or complete. They all come, with their own limitations. But most of the rockfall inventories that have dealt with a number of rockfalls that are larger than or similar to what we've had, so I'm talking about 300 rockfalls, have been able to actually produce very robust power law relationship and have been able to see this power law relationship. So not necessarily using TLS, measurements of the data, but also just looking at rock historic inventories. For Lauterbrunnen, we don't have historic inventories, or the historic inventories are not very robust. So we have to rely, in this case, really on what we can measure now and try to fill in the gaps with very few data points that we have in the last, 100, 150 years ago. So in such a case, when you really don't have anything else to work with, a data set of 5 years is definitely, a really good start. And I would say, since we haven't really seen a difference between the 1-year data sets and 5-year data sets, the frequency magnitude relationships are almost identical and they agree with one another. This is a good place to start. I wouldn't say this is very robust, and of course it can be improved and it should be improved as we collect more data. That's why we continuously monitoring this rockfall activities, but it's a place to start. And we basically use this 5-year data set then to come up with a return interval of larger events. Yeah, so we came up with an interval of large events more than 2,000 to 3,000 cubic meters, so way larger than what we have actually detected. Remember, the largest one that we detected is about 260 cubic meter. But we use this parallel relationship to really extrapolate about the frequency of much larger events, and that number was 3 to 6 years. And we were all very surprised because that's not long, so every 6 years, if you're going to have an event of over 10, over 1,000, potentially 3,000 cubic meter, this is not a very long time. And actually, when I was done processing all the data and submitted my paper for publication, when the paper was in review, there it happened. We got the event that was about, I think, nearly 3,000 cubic meter. And we've been monitoring for almost 5 years, right? So it's coming to that end, and then we get that event. Of course, this doesn't prove anything. It could be, as you said, it could be that due to the stochastic, nature of Rockfalls, and we just got lucky. But it's a good place. It's good to see that actually, for this at least, it helped. And only with more observations, we can improve its robustness. But you're absolutely right. With short-term inventories, especially when they're not complete, and in this case, we are also not complete, not just because we don't have long and large events, but we're also missing all the little events because of the detection limitations of the scanner. So definitely not a complete inventory, but you can still do a lot with incomplete inventories and just continue monitoring and improving it. For monitoring rockfalls, I think in the Pamir, in the Hindu Kush, or anywhere else, my understanding is that there's a lot of effort that goes into creating these inventories, and that's really great. We may not be able to do much with them right now, but if we consistently and systematically monitor these rockfalls, years to come, we can actually produce these robust frequency magnitude relationships and use that as a way to forecast larger events. So I would suggest that, as you mentioned, we focus on developing this longer term and more complete and systematically collected inventories so that we can make such extrapolations with less errors. I hope I answered your question.
Yes, thanks, Solmaz. Sorry, I just want to clarify. I'm not questioning your research method or research duration. That's common limitation in any research project we do. We do not have enough funding or enough research life to spend many years on sampling one place or few places and then come up with robust idea. But what I would like to see, we acknowledge that limitation in any publication, in any presentation, which you did. I just repeating the same things. So we have to, or we need to start from somewhere and keep collecting more data. Maybe after 50 years, 100 years, there will be a good accumulated enough data for others to come up with robust equation or predictions of any stochastic event. Thank you very much.
Thank you, Ben. Just to add to that, I think this is something that I haven't seen being done in Central Asia, and it's something that I'd like to bring to Central Asia, or at least support those who want to do a study like this, is that once you have the scanner, actually, there was no funding for this 5-year project. There was no funding for it at all. We had this scanner, which is really a big help because you have equipment, but then, you have your master students, your PhDs, your postdocs, that they go there, every 2 months or so, and they do the measurements. In this case, we have to drive about 6 or 7 hours to get to the study site. But I think in many places, at least in the Pamir, once, for University of Central Asia being best, being positioned in the heart of the Pamir, it would be a lot easier, I think, to access sites. So once we have, the equipment, if that investment happens, Then students can be trained, and they can really play a major role in continuously monitoring sections, or areas, specific areas near villages, places where we think the impact would potentially be high for over a long time. I adopted this project from someone else, and 4 other people adopted this project from me here, and they're all students, So this could be something that can be handed from one student to the next, and I think this is a win-win situation, because the students also benefit. They learn technique, they can use it for their thesis, for their small research projects, and at the same time, the faculty and the community really benefit from the kind of data that is needed for reducing hazards.
Okay, thank you very much, Solmaz. We have a question from Hengoma, or student. Hengoma, please.
Hi. I was wondering, is the inclined slope more dangerous in rockfall activities as the object gains speed while it's falling? In general, I mean, what slope is more dangerous considering rockfall activities? And are there different mitigation processes considering these different slopes? Because in steep slopes, we cannot plant trees. And then in the incline slopes, there is more speed gaining when the rock fall.
Exactly, and Hengoma, you answered your own question, I think. So this is, you're absolutely right. So when you're looking at, vertical walls, oftentimes the materials that are detached as rockfall and fall as rockfall, they don't travel great distances. They simply get detached and they fall. If they land on a steep, this is the talus slope. So if the talus slope is inclined and have some kind of a gradient, then they can travel and topple along the talus slope. But generally, they don't travel really far behind. But there are a number of different factors that should be taken into account. So if you have a very large material, it could fall and just get deposited immediately, maybe bouncing a couple of times off other parts of the wall, if there are overhanging sections in the wall. But something that is maybe not so small and not so big, has the potential to travel a little bit more further. So the slope definitely plays a role here. In terms of mitigation, what we can do, I think there are by far more people in this audience that can advise on mitigation strategies for what can be done. One idea would be just to have zones that you look at, previous historic rockfalls. So in Lauterbrunnen, in this case, you see where previously fallen pieces of rock wall have landed. And you can assume, and again, sometimes it's a good assumption if you're looking at really large boulders, because you can assume that they probably didn't move after it landed. With the smaller ones, you cannot make that assumption. But by looking at where they have landed previously, that's the evidence that will help you for future mitigation. You will know that you are within the rockfall zone already. Yeah. So if you are doing development, or if you already have houses that have been built there, you have to really think about how to protect those, either by relocation, which is generally, I know this is not really the case in the Pamir and other places where space are limited and one cannot easily relocate villages from one place to another, but mitigation strategies that can be placed, such as protective walls that can be built to protect houses and infrastructure.
Okay, thank you very much, Solmaz. We have a question from Khulik Nazar. Khulik Nazar, please.
Thank you, Mohsin. Thank you, Solmaz, for bringing, or let's say translating this complicated problem into language of mathematics. I have seen some very simple but interesting equations, formulas there. Could you please go to the slide where you have the relation between n and v? N is dependent on v. And then how did you find 2 coefficients there? It was on the top, I guess. No, it's...
Yeah, it's coming up. I know what you're talking about. I think that the power law equation. Here?
Yeah. No. Yeah, next, I think.
Next?
No, next. Yeah.
Oh, hold on. I think this is where what you're looking at, right? The A and B here?
No, yeah, here we have A and V. So V represents the horizontal line here, and N is vertical. Am I right?
So you have the volume, yes, on the x-axis, and then you have
Yes.
the N, basically the cumulative number of events per year
Yeah.
on the y-axis. And what you're looking at here, these are basically non-linear regressions through the data points. So what we did was, after removing all the volumes that are less than the rollover volume, we basically just fit a lot of non-linear regressions through these data points using the range that we have for rollover volumes. So we started, let me just go one back so this becomes more clear. So here I said that the rollover volume, that it's not just one point. Many people think about it actually as one point below which you don't have this linear relationship anymore, and your data starts to deviate from it. But in our study, we did it a little bit more robustly, meaning that instead of picking one point as where we have this change from linear to some form of deviation from linear relationship, we chose a range. So we basically fit nonlinear regression lines through the data points using this range of volume. So for every value that falls between these two lower and upper bounds of the rollover volume, we calculated a nonlinear regression. And basically your exponent B is more or less the slope of that line that you get. So here where you see the upper and lower lines here that are shown here in blue, they basically correspond with the nonlinear regression that is associated with the maximum and minimum rollover volume. That's why you get a range here, as opposed to just having one line.
Okay, then this coefficient in front of V, it's negative. Am I right?
Yes, because you have a negative power law relationship here. So if you had a positive power law, it would be basically pointing the other way around. So it would be like something like this.
Okay, thank you.
My pleasure.
Okay, thank you very much, Solmaz. Is there any other question? No? If no question, I would like to ask a last question, Solmaz.
Of course.
Okay, thank you very much, Solmaz, for a very interesting talk. I enjoyed it very much. And this is a general question for actually people working on the rockfall. Is there any relation between studying rockfalls, as you studied here, with field relations? I mean, the structures in the field. So if you go there, probably you see some faults or joints to the faults. And also probably you were talking about these Mesozoic limestones. But I don't know if these limestones are homogeneous at all parts, or you can find, I don't know, some pelitic, or I would say clay-rich interlayers or sandy interlayers, and how these real field observations will be considered as variables in the equations you are talking about and studying the rockfalls.
Very good question, Mohsen. Thanks for that. With the limestone, this is uniform lithology, so it's not interbedded with anything else. So the whole valley has a uniform lithology, which is limestone. And that's why we also chose this valley, because we wanted to rule out lithology as a triggering factor for rockfall studies. That was one of the main reasons. The other reasons was that these rockfalls are free of vegetation, so this is easy to monitor rockfall activity. But going back to your question about joints, fractures, this is definitely one of the areas that we have to do better and we have to really study. Unfortunately, with such steep rock walls that almost a kilometer in height, it's very difficult to basically get very close. You can get close to some sections of the wall which are right above the talus slope, and basically do some manual measurements of, fracture densities, and try to then extrapolate that to the rest of the wall, which might not be a very bad way to do it, but it's just one way to do it when you're so limited by the steep slope. But now recently, our group is trying to get a permit to fly a drone up these walls, and I think very soon they should be able to do that, so that they can get high resolution imagery very up to the middle, to the higher up sections of the wall, of the fractures and the kind of fractures that we see there, because we do actually see fractures there. We do see joints, and it would be very interesting to look at the rockfall locations and see if there's any correlation, between where we see these rockfall or certain volume of rockfalls associated, with joints or not associated with joints. And we have a student, two master students that are working on that. And so far they are using the TLS data, so the data that we have already collected. So again, you can use this data for so many different projects. They're using that to extract fractures and jointing patterns from the rock wall surface, and then basically see if there's any correlation with the locations of the rock falls detected over the last 5-6 years. This is one of the most important, I think, studies, because when we looked at other triggering mechanisms for rock falls in Lauterbrunnen, including weather-related mechanisms, as well as seismicity, we didn't find any correlation, any strong correlation, let's put it that way. But I have this sense that we will find some strong correlation with the jointing patterns on the walls. And hopefully we'll have some answers on that soon.